Okay, so we're going to continue that problem from last class. So it was about a football that was being kicked at an angle of 37 degrees or something. Okay, so pull that back up out of your notes and kind of get looking over that again. Let's refresh our memory on what we did. In that last problem, we had a football that was kicked at an angle of 37 degrees. We had an initial velocity. We found the maximum height and the total time that it traveled. Okay, so let's talk first about this initial velocity vector. What did we have to do to the initial velocity vector? What did we do to that 20 meters per second at 37 degrees? Yeah, we had to break it down into components because we don't like dealing with things in angles. Okay, so whenever we're given an initial velocity at an angle, we've got to break it down into its components. Okay, and we did all that. Its components then, what were the variable names for those components? V sub x, V sub xo, and V sub yo, okay, because they were initial velocity vectors. Okay, once we solve those components, what do we do with the 20 meters per second? Do we use it again? No. Okay, once we're done with that, we're done. All right, so let's take a look at this next example here. We're going to look at that same problem, but we're going to assume this time it was punted from a distance of 1 meter off the ground. So instead of starting at ground level, it's punted from a meter off the ground. Okay, how far did the football travel before hitting the ground? We're going to set basically our origin this time. We still set our origin where the motion starts. But this time, it's going to land a meter below where it started. Okay, so let's say that that purple line is its origin. That's where it's leaving that guy's foot, but it's going to land a meter below where it started. Okay, so that's going to change which variable for us? Y. Y. Okay, it's going to change our final vertical displacement. And what will the value for Y then be? -1. Good. -1 meter. Because we're going to land a meter below where we started. Okay? So what's our overall goal here? We're trying to answer the question, how far did the football travel? So that means we're solving for which variable? X. Good. We're solving for horizontal displacement, which is X. All right. We know from the last problem our initial velocity vectors. Okay, so let's go ahead and just reuse those. Those don't change. It still was kicked at the same angle with the same speed. The only thing that changed was the height from which it was kicked at. Okay, so tell me those initial velocity vectors that we found last time. What was V sub yo? 12 meters per second, and V sub xo was 16 meters per second. Okay? Those are the only things that we can keep the same. Okay? We're still going to have to solve now for time. Okay? Because that 1 meter difference is going to make a difference in the time that it's in the air. Okay? So, first of all, if we want to solve for x, we can use our horizontal equation, x equals V sub xo times t. Right? So let's get your equation sheet out if you don't have that out already. Equation sheet and calculator. The only way we can solve for x is using the equation V sub xo times t. And we don't have time. So we need to go about solving for time using our vertical equations, right? Time is our only variable that can go between horizontal and vertical. It's the only connector between those two. All right, so let's go ahead and solve for time here. Which equation could we use to solve for time? Can we use this one? Y equals y sub o plus vyot 1/2 gt squared? Yeah. We can use this one. We can have all of those components. Y we know is -1. Y sub o is 0. V sub yo is 12 times t plus 1/2 negative 9.8 t squared. So what are we going to have to do here to solve for time? We got to use a quadratic. Okay, so that's going to leave our quadratic equation at negative 4.9 t squared plus 12t plus 1 equals 0. Okay, because I'm going to move this 1 to the other side. Okay, so we need to use our quadratic formula to solve here for time. Okay, so by solving our quadratic, I got my time to equal 2.53 seconds. Do we agree? Okay, from the quadratic, you got two answers, one of which was negative 0.08. Why can that not be the case? Time cannot be negative. Okay, so whenever we get a quadratic with two answers, one of which is negative, you have to go with the positive answer. What if you get a quadratic that gives you two positive time answers?
The second one, bigger time.
Depends on what you're looking for. Okay, if it asks you for the time at 6 meters, that means it's hitting 6 meters on the way up and on the way down. Okay, but if you're asking for final time of the whole thing, yes, you would look at the bigger one. Okay. If that was the case, if you were looking for the whole time, it wouldn't give you two positives. But the only time it would do that is if you were looking at a specific displacement. You'd be able to know that it's hitting it on the way up and on the way down. Okay? 2.53 seconds, good. So then we go ahead and solve for x equals v sub x o times t. So we'll take 16 times 2.53 seconds. And we get a distance of 40.48 meters. Let's say that I throw a ball at an angle of 24 degrees and it has a velocity of 14.2 meters per second. Okay, I want to find out its peak height. And I want to find out how far it traveled. This side could be labeled what? V sub x o. All right. V sub y o because that's the vertical component of our initial velocity vector. This is the horizontal component of our initial velocity vector. So we're going to go ahead and break those down. V sub x o is going to be our hypotenuse, 14.2, times sine or cosine? Cosine. Our V sub x o is adjacent to that 24-degree angle. So 14.2 cosine of 24. Make sure that your calculator's in degrees. Okay, V sub yo, I'm going to take hypotenuse times sine of 24. Okay, do we agree with those components? 13 and 5.78? Okay. So let's talk about what else we know here. First of all, let's start with our peak height question. What variable are we solving for if it asks for how high does this object go? What variable? Y. That's our question mark. What do we know specifically about an object at peak height? We know that V sub y equals 0. Very good. Okay. Our final vertical velocity at peak height is 0 because it pauses for that instant. Okay, at its very peak height. All right. So, do we have enough information there to solve for our y? I think so. using the equation Vy squared equals V sub yo squared plus 2gy. Okay, so 1.70 meters there. We've answered our first question. Now if we want to find how far it's traveled, that means what variable are we looking for? X. Overall, we're looking for X. We need what other variable to solve for that? We need time. Okay, we have to have time in order to solve for the total distance, the total horizontal distance traveled. This time, what's the simplest way to solve for time? Let's use our first equation to solve for time up to peak height, and then we'll be able to multiply that by 2 since our motion is symmetric here. Okay, since we're landing at the same height we're starting at. Okay, so we can use V sub y equals V sub yo plus gt, and this will get us our time at our 2 peak height. Okay, so at peak height, your final vertical velocity is 0, 5.78 plus negative 9.8 times t. That gives us a time at peak height of 0.59 seconds. Yeah? And don't forget that we need to multiply by 2. So our total time for our entire trip is 1.18 seconds. We could have also used the equation y equals y sub o plus vyot plus 1/2 gt squared and solved for time. Okay, because our final vertical position and our initial vertical position both would have been 0. We would have had to use the quadratic to solve for that, though. Okay, so this way is a little simpler since our motion is symmetric. Okay, so to find x, we're going to plug in x equals v sub xo times time, which means we're going to take 13 times 1.18. And we get a total distance traveled of 15.33 meters. So this is a rolling projectile. Let's say that we set our origin here at the top of the table. Okay, the table height is 1.3 meters. We're going to say that this marble's rolling off the table, and it has an initial velocity of 2.14 meters per second. Okay, it has an initial velocity of 2.14 meters per second. Is that initial velocity v sub xo, v sub yo? V sub xo. Okay, anytime we have a rolling projectile or something that's going off a cliff or off some sort of, I don't know, thing like this, say something that's rolling off, it only has an initial horizontal velocity. Its vertical initial velocity is 0. Okay, so we know v sub yo for rolling projectiles is 0. Okay, I want you to tell me what this distance is right here. I want you to tell me how far from the table is it going to land? How far from the edge of the table is it going to land? Okay, that means we're solving for which variable? X, good. And what does the 1.3 tell us? tells us y, and that tells us it should be negative 1.3 meters because we're ending up 1.3 meters below where we started. Okay, so what do we need to look at here? We've got to find time, right? In order to find x, we have to have v sub xo, which we have, but we don't have time. And what equation can we use to solve for time? Yep, we can use y equals y sub o plus vyot 1/2 gt squared. We know y is equal to negative 1.3. In rolling projectiles, both of these terms would be 0 because we know v sub yo is 0, we know y sub o is 0. So for a rolling projectile, both these terms can be dropped. Okay? So we're just going to have 1/2 negative 9.8 t squared. All right. From there, we're going to take our time, plug it into x equals 2.14 times 0.52. I guess everyone agreed with my time, right? 0.52 seconds? All right, good. Okay, that means the marble is going to land 1.10 meters away from the edge of the table. Chapter 3, which is called Relative Velocities. Relative velocities. Relative velocities are a fancy way to say these are velocities based on your observation with one another. Okay, so observations made in reference and their relationships to each other. Okay, so I'm going to talk through what we kind of see relative velocities like in real life, and we're going to do a couple examples here. Relative velocities is really just about building a triangle, right? Writing your components down and having the correct resultant. That's all relative velocities is being able to look at basically two objects, seeing how they relate to each other, and looking at the resultant between the two. Okay? So, for example, if I have two trains traveling 80 kilometers per hour toward each other, okay, toward each other. They're traveling and they're coming toward each other. If someone's standing on the tracks, standing still, they see each of those trains has a velocity of 80 kilometers per hour. You don't have to necessarily write this example down. I'm just going to talk through it so you can kind of get an idea about what relative velocities mean. Okay? Someone standing on the tracks, if they could measure that in their, brain, if they can calculate that and see that, they're going to see they're each traveling 80 kilometers per hour, or they're each at least traveling about the same speed. Okay, they'll be able to see that because they're standing still on the ground. Okay, they should be able to see that they're each traveling about the same speed toward each other. If someone's standing on one of the trains that's moving 80 kilometers per hour toward this other one, okay, so if I'm standing on one of the trains, it's going to seem to me like the train coming at me is traveling twice that fast. Because I'm traveling 80 kilometers this way, it's traveling 80 kilometers per hour at me. Okay, so it seems to me that it's traveling twice as fast. I'm approaching, or we're approaching that distance twice as fast because I'm moving and the train coming at me is moving. Okay, so that's all that relative velocities really mean, is that depending on your location, things look different, things seem to be traveling a different speed. Okay, so if I'm going 70 down the interstate and I pass a car that's going 55, how fast to me does it feel like they are going? Okay, or how fast does it feel like I guess I would be going? it seems like I'm only going maybe 15 miles an hour faster, okay? Or if I'm the one traveling 55 and someone passes me going 70, it seems to me like they're traveling 15 miles per hour because that's the difference between our two velocities. Okay, does that kind of make sense? When someone's going in straight lines, we're just looking at either addition or subtraction depending on whether they're coming at each other or they're going in the same direction, okay? So if I come up on a car that's traveling way slower than me, it seems like they're going 5 miles an hour, but it's really just that they're going 5 miles an hour slower than I am. Okay, that's why it seems like it's such a drastic difference, but it's really not. Okay? So if we have same line velocities, things that are traveling in the same plane, right? We're both going north, we're both going south, or one's going north and one's going south. They're coming at each other. We're going to use simple addition or subtraction to find that relative velocity. Just like the trains that were coming at each other, we're going to add those velocities together. If they're going apart from each other, we're going to subtract them. Okay? We're going to look at the difference between those two. If something's not moving in the same line, if we have them coming from different directions, we're going to have to use vector addition. Okay, so main examples we use here is if a plane is flying and there's a wind current, it's going to be pushing them in some angle, right? They might be trying to fly true north, but there's a west wind that's blowing them a little bit to that direction, okay? That's a good example of relative velocity. They might be trying to fly exactly north, but they've got to compensate for that wind. That's their true velocity, okay? Or swimming in a river is a good example for this. You're trying to swim against the current, but the current's pushing you a little bit as well, okay? So those are kind of the main examples we'll use to demonstrate relative velocity. But we're going to have to make sure that we draw our components and our resultants with the correct format and in the correct direction. Okay, so for relative velocity, it is really important that you draw the diagram to demonstrate the motion. So we're going to be careful with labeling, and we're going to be careful with determining what our resultant should be. Okay, so our resultant should be our overall goal here, or what this object's trying to do. And we're going to look at this problem here in just a second. That hopefully we'll be able to see the resultant a little bit better. Okay. But with relative velocities, it is important that you draw your vectors, you add them tail to tip, and you're trying to find that resultant or that hypotenuse or whatever the resultant comes to be of this particular problem. Okay? So I'm going to put a diagram up here of a boat crossing a river. Okay, and we're going to look at what the current does to it, what its goal is going to be, which is always its resultant. Okay? So this says a boat needs to travel straight across the river that has a current flowing 1.2 meters per second west. They leave the shore at a speed of 1.85 meters per second. What's the actual velocity of the boat? With what angle from the shore must the boat be traveling in order to achieve its goal of ending up straight across from where it started? Okay, so this boat's overall goal, here's this little boat on the shore. Its goal is to get across the river, straight across at a point from where it started. Okay. So this means velocity of the boat with relative to the shore. This means velocity of the boat relative to the water. Okay, how fast it's traveling and where it's traveling in the actual water. This is talking about relative to the shore. Your book goes into a big long description about how to describe these vectors with two subscripts. I don't use that near as much. Okay, I kind of use my own labeling system or what works for me, and that's what I would encourage you to do too. Okay, they go into a big discussion about using two variables or two subscripts to label with respect to each other. I don't do that, so you can, if you want to look into that, you can. That's usually not how I do it. Okay. What I'm looking at here is that my water current is pushing me west. Okay. So I've got a current that's traveling west at negative 1.2 meters per second. Okay, or the negative just tells me west. I'm leaving the shore at a speed of 1.85 meters per second. So where does the 1.85 go? Which side of our triangle here does it go toward? The hypotenuse side or this side right here? The hypotenuse side. Very good. Okay, and it goes there Because our overall goal is to end up straight across from where we started. So out of these three vectors, which can you tell is the resultant vector? The black line, the yellow line, or the green line? The black line. Why can we tell it's the black line? How can we tell which is the resultant just based on the diagram itself? Go, Katriana, what do you think?
It starts at the origin and then the tip goes to the end.
Exactly. If ever we see a tip that touches another tip of a vector, we've got to know that's our resultant right there. Okay? So our resultant is the overall goal of our motion here. We want to end up straight across from where we started. Okay? And if our current's going to push us west, that means we must leave at an angle this way somewhere. Okay? We've got to head out northeast if we want this current to push us west straight across from where we started. Okay? How does that feel? Okay? You all right? All right, so let's solve for our resultant here. We want to find exactly what speed we're traveling in the water, and we want to find exactly what angle we needed to leave the shore at. Okay? So let's solve for this side of our triangle here. How would we do that? We can use Pythagorean theorem, right? But we already have our hypotenuse. So it has to be 1.85 squared equals 1.2 squared plus v squared. So I got the velocity of that boat is actually moving at a speed of 1.41 meters per second. Okay, that's its actual speed relative to the current, relative to its actual, what it thought it was leaving at. It's actually moving at 1.41 meters per second. And what's the angle that it had to leave the shore at if it wants to end up straight across from where it started? Is that what you had? Yeah? Or no? Okay. And this angle would be blank of blank. What do we have? East of north. Very good. East of north. It's touching the north axis. So here's our axis right here. It's touching north. Did we go east of north or west of north? We went east of north. Very good.